Today, we're going to start a new topic in our aging course, and that's the topic of learning and conditioning. We'll begin by taking a brief look at classical conditioning. And as you'll recall from your introductory psychology class, classical conditioning represents one of the most basic forms of learning. It's a process that establishes an association between a reflexive response and a previously neutral stimulus. And it begins with the initial conditions in which we have to find an already existing unconditioned stimulus and an unconditioned response pairing, such that when we know that when that stimulus is given, we will always see it elicit a particular response. So, for example, in the case of the famous experiments of Ivan Pavlov that we all learned about earlier in our introductory psychology classes, the unconditioned stimulus would be the food that was presented to the dog, and the automatic, built-in, or innate, if you will, response to that food stimulus, the unconditioned response, would be salivation. So Pavlov knew that whenever he presented food to a hungry dog, the dog would salivate. So that's our initial conditions. We set up an unconditioned stimulus, a UCS, that is paired with or always elicits an unconditioned response. So now once we've established this or identified this UCS, UCR pairing, we can then begin the conditioning process. And in the conditioning process, what we do is we repeatedly present a neutral stimulus or a conditioned stimulus, as it's known within the paradigm, is CS. We present it repeatedly in association with the unconditioned stimulus. So again, in the case of Pavlov's dogs, Pavlov used the bell. So what he did was he would present the bell shortly before he presented the food, and then the food would give rise to the salivation response. So conditioning occurs when, after you've paired this previously neutral response, the conditioned stimulus, with the unconditioned stimulus, many, many times, what eventually happens is the nervous system is modified, and eventually presenting the conditioned stimulus by itself will give rise to the targeted behavior, in this case, the salivation response. And that's the point at which we know that a classically conditioned bond has been formed, when the conditioned stimulus, the previously neutral stimulus, in this case the bell, will elicit the targeted response, in this case salivation. There are many different variations of the classical conditioning paradigm. What I presented on the screen in front of you are two very common ones that are employed. So let's first take a quick look at what we call the delay paradigm. And in the delay paradigm, what we do is we present the previously neutral stimulus, the conditioned stimulus, in Pavlov's case, the bell. We present that stimulus before the onset of the food stimulus. And in the delay paradigm, not only does the conditioned stimulus occur before the presentation of the unconditioned stimulus, but it overlaps as well, as you can see represented in this time diagram. The delay paradigm is probably the most efficient of all of the classical conditioning paradigms. By efficient, I mean it's the paradigm where we'll take the fewest numbers of trials to establish a new bond between the conditioned stimulus and the target response. And once established, it'll be the most resistant to extinction. And there's another paradigm that's important for mostly theoretical reasons, and that's the trace paradigm. And again, in the trace paradigm, just like the delay paradigm, the conditioned stimulus, the previously neutral stimulus, always precedes the onset of the unconditioned stimulus. However, there is a gap between the offset of the conditioned stimulus and the onset of the unconditioned stimulus, and that's called the trace interval, as you can see in this diagram. And as the trace interval gets longer and longer, conditioning becomes more and more difficult to establish. And what we will see in a moment is that older organisms have a very, very difficult time being conditioned with the trace paradigm. And the one thing we should always note, and Pavlov was very, very clear on this, is that for classical conditioning to occur, the conditioned stimulus has to precede the onset of the unconditioned stimulus. In fact, that was so important for Pavlov, he called his theory the second conditioning system, the second signaling system, I should say. He thought the whole role of essentially the conditioned stimulus was to serve as a signal that the unconditioned stimulus was going to become available. And that's why essentially the nervous system evolved to be able to form these new links to previously neutral stimuli. So sadly for us gerontologists, almost all the research regarding classical conditioning and aging has relied upon animal models. And what has typically been found is that when the trace paradigm is used, older mammals like cats, rats, and rabbits demonstrate very, very poor acquisition with respect to the classical conditioning paradigm. However, and that's actually can be demonstrated in this figure that I presented up here on the screen. In this experiment done by Diane Woodruff Pack, what we see is that when animals were presented with 126 conditioning trials a day, it was found that young rabbits established a strong classically conditioned response in 3 days. Middle-aged rabbits took 9 days to establish their response. And the older rabbits, the very oldest rabbits, took almost 12 days to respond to form the conditioning. In other words, 4 times longer than the young animals. However, but remember, that's with the trace paradigm, and in this case, the trace delay was 500 milliseconds. When you use, if you will, the delay paradigm, what you find is indeed that older animals can be conditioned much more efficiently than we see in the current graph. But the acquisition still requires many more trials than we see in their younger animal counterparts. Fortunately, we do have a few studies that have examined humans with respect to the classical conditioning paradigm. And they all sort of tell the same picture. And most of them have used as the unconditioned stimulus, unconditioned response pairing, the corneal air puff eye blink, if you will, stimulus response pair. Those are innate pairings. If you put a puff of air into someone's eye, you'll automatically elicit a blink from them. So that's a stimulus response pairing that's innate, that's built into the system. And if you use a previously neutral stimulus like a tone, what you can find in the conditioning paradigm is that eventually the previously neutral tone or conditioned stimulus will be able to elicit an eye blink. So the study I want to describe for you here again was done by Diane Woodruff Pack, this time using humans. The human observers were four different age groups with mean age of 20, 45, 53, and 73 respectively. Again, the UCS-UCR pairing was a corneal air puff delivered to the eye and the reflexive eye blink, and the conditioned stimulus was a tone. They used a delay paradigm, that is where there was no gap between the onset of the, if you will, the conditioned stimulus and the unconditioned stimulus, and there was an overlap between the two stimuli. There were 108 trials total in this study, and on every 9th trial, the essentially unconditioned stimulus, in this case the corneal air puff, was omitted and just the tone was sounded. And the dependent variable in the study was on how many of those tone-only trials was an eye blink observed. And you can see by the results of the histogram here that there was a significantly weaker acquisition of the classically conditioned response in the older humans in this study. After 108 training trials, the 20-year-olds were showing a very strong acquisition. They were showing the eye blink on about 70% of the tone-only presentations. But that big drop below 60% for the 45-year-olds. People in their 50s dropped below 40%, and by the time you got to the people in their 70s, they were approaching 30% in terms of the proportion of, if you will, conditioned stimuli that were eliciting the target eye blink response. And what's particularly interesting about this curve is that we see that not only does classical conditioning become weaker in older adults, that it starts not just in very late life, but as we see here, as early as in our 40s. Studies similar to this study with humans in classical conditions have also revealed that there tends to be less resistance to extinction. That is, when you begin to present the conditioned stimulus by itself and you do it over and over again without refreshing the link by presenting the conditioned stimulus together with the unconditioned stimulus, what happens is the trace in the nervous system begins to fade. And that extinction curve is also seen as a measure of how strong the conditioned response is. So in the case of older adults, both the acquisition curve and the extinction curve are flattened out, showing that classical conditioning is indeed quite weak in older adults, including in older humans and older animals. And before I leave this topic of classical conditioning, we can do a little bit of speculation here based on this note I have in green on the bottom. And that is, at the same time, it's been noted that older people are weak in terms of classical conditioning processes. They're much more difficult to condition. Older persons also seem to be less susceptible to developing phobias, that is, irrational fears. And the most common model of how phobias develop is a model based on a classical conditioning type of mechanism. So it's actually not surprising that weaker classical conditioning in the older population is concomitantly associated with a diminished frequency of phobias. That hasn't been scientifically demonstrated to my fullest satisfaction, but there's evidence that such a link does indeed exist in the literature. So now let's turn our attention to another basic or simple form of learning, instrumental conditioning. And this form of conditioning refers to the modification of voluntary behavior as a consequence of things that happen in the environment. It is indeed the instantiation of Thorndike's law of effect that, again, we learned about in our introductory psychology course, and we saw B.F. Skinner's, perhaps Skinner boxes and the schedules of reinforcement that he used to train behaviors in rats and other animals. So we see this modification of behavior due to environmental consequences. And typically we talk about those environmental consequences being divided into reinforcements, that is, groups of stimuli that increase the probability that the associated behavior will be emitted in the future, and other types of stimuli that decrease the probability that those behaviors will be, if you will, emitted in the future, and those are punishments. Reinforcements increase probability of behavior in the future. Punishments decrease probability of behavior in the future. And we typically measure the strength of instrumental learning based on the rate of extinction and on the rate of acquisition. In many ways, quite similarly to the way that we measure the strength of classical conditioning. In a nutshell, the effects of aging upon instrumental conditioning tend to be quite small. We see in both animals and in human studies, and again, the preponderance of the evidence is with animal studies, we see that acquisition rates of behaviors essentially occur with a little bit slower progress in older animals than younger animals. But I want to emphasize that it's just a moderate decline in the rate of conditioning. And most studies have shown that extinction rates tend to be comparable to the young in older animals. So the indicators of how strong instrumental conditioning might be seem to suggest there's only a small incremental effect in older adults. However, there's two kind of special modulating factors that influence instrumental learning and its related behaviors that we need to take special note of with respect to older populations. One of those factors has to do with changing base rates of behavior in older populations compared to younger populations. I'll explain that a little bit more in just a moment. But another factor that's qualitatively distinctive is a phenomenon of behavior known as response perseveration or behavioral rigidity. And I'll talk a little bit about that first in the context of an interesting rat study that was done, an animal study. And then I'll try to build an analog to that study in human behavior. So let's begin by looking at this base rate of behavior problem. First, we have to consider the fact that in instrumental conditioning, unlike classical conditioning, the behavior has to occur before it can be conditioned. Remember, in classical conditioning, we can make the target response occur anytime we want. We can make the dog salivate anytime we want by presenting food. We can make an individual blink anytime we want by putting an air puff in their eye. But in the case of instrumental conditioning, we have to wait for the behavior to occur before we can either punish it or reward it. So it therefore follows that the more behaviors an organism emits per unit time, the more opportunities there will be to implement a reinforcement. And similarly, the fewer behaviors they emit per unit time, the fewer opportunities there will be to reward or punish the target behavior. So this number of behaviors that are spontaneously emitted per unit time is what we're referring to when we talk about the behavioral base rate. And with respect to older animals, including older humans, what we find is, for a variety of reasons, the base rate of behavior is significantly reduced. Older animals and older humans simply emit fewer, if you will, behaviors per unit time. So as a result, older adults experience fewer opportunities to be rewarded or fewer opportunities to be punished in a given time period compared to their younger counterparts because of this general, if you will, reduction in their rate of behavior. And there's a consensus opinion among people who study these types of things that much of the decrease in the acquisition rate that we see in older animals, including humans, in the instrumental learning context, appears to be due to these lost opportunities that result from this overall lower base rate of behavior. So I want to follow up on this problem with base rate of behavior to talk a little bit about a classic study that was done to try to modify a simple schedule of reinforcement to try to get around the base rate problem in older animals and therefore increase the rate at which a target behavior could be learned. And so let's begin with the idea of a very, very simple schedule of reinforcement. About the simplest one we could think of would be one like this, that we have a target response that we call the correct response, and any other response would be considered an incorrect response. And so what we would do is every time the correct response occurs, we reward it. And every time the incorrect response occurs, we withhold the reward. We don't reward it. With that simple schedule reinforcement, eventually what we typically see is the rate of behavior on that targeted response will go up over time as a result of being rewarded. Again, Thorndike's law of effect. Leach and Witta, two researchers in 1971, set up a very interesting learning experiment where young and older participants could make three different types of responses. They could either make a correct response, or they could make one of two types of errors. They could make a commission error, that is, they made a response, but it was the wrong response, or they could make no response at all during the prompting condition, and that would be an omission error. And so now what they did was they essentially modified the schedule reinforcement based on this little table I present on the slide in front of you. For correct responses, they were given a full reinforcement. Let's say, for the sake of example, they were given a dime every time they made a correct response. And whenever they made an omission error, they got nothing, no reward whatsoever. But interestingly, if they made a commission error, that is, as they made a response, but it was the wrong response, they still got a reward, but it just was only 1/3 of the value of the correct response. Maybe they got 3 cents instead of a dime. And with this modified schedule reinforcement, what they found was they could simultaneously increase the rate of behavior in their older animals and also increase the opportunity for the correct response to occur and therefore being reinforced. And in the long run, they found that this modified schedule reinforcement could offset the base rate behavior problem observed in their older human observers and lead to more efficient and quicker acquisition of the targeted behavior that they were training. And so this is really quite an interesting outcome. There's a downside to these types of procedures, however, and almost all of them that have been devised, that is special schedules of reinforcement to get around the base rate problem in older animals and older adults. What you usually find is a cost on the other side of the age spectrum. Whereas you increase the acquisition rate for the older adults, what you do is you tend to slow the acquisition curve down a bit for the younger animals or the younger adults. So that's something that you have to keep in the back of your mind if you're ever considering the potential opportunities to apply these modified schedules of reinforcement in an instrumental training situation. So in addition to the base rate problem, I did identify earlier one of these special factors that is interesting with respect to the instrumental conditioning or instrumental learning context. And that was a phenomenon known as response perseveration or response rigidity in humans. So I want to describe to you what I think is a really fascinating study that was done by Goodrick way back in 1968 that essentially looked at a very sort of unusual outcome of response perseveration in these older animals. So the first thing we have to note here is that many researchers have noticed that older rats have a strong tendency to perseverate previous behaviors during maze learning. That is, they stop, scratch their head at a particular spot. They're likely to stop and scratch their head at that particular spot again in the next time through the maze. There's something qualitatively different about their behavior compared to younger animals. And this type of behavioral inertia is called response rigidity in the gerontological literature writ large. In Jack Botwinick's famous book, Aging and Behavior, there's a whole chapter called Response Rigidity where he talks about these type of phenomena. So what Goodrick did was he devised an intriguing study that was designed to translate these age-related increases in response rigidity into an advantage for his older rats. And what he did was he used a T-maze type of learning, and in front of us we see a T-maze. This is not the T-maze that Goodrick used. I just drew this for the sake of demonstration, but you can see in this maze how a rat placed in the start box could go through the maze and successfully find his way to a reward, and that is typically food in the goal box. So what Goodrick did was he built this type of T-maze, but he used a special, if you will, modification to the T-maze that was designed so he could manipulate their behavior, the young and the old rats' behavioral experience on the very first trial. And he did that by using these special spring-loaded doors at each T intersection. So as the animal came up the alley and came to the choice point where the animal had to turn left or right, what the animal encountered were these two spring-loaded doors. And on the one on the left, what the animal could do was use its muzzle and push the door open and proceed to go to the left. Or the animal could have come up to this door on the right and pushed its muzzle through and essentially proceeded to the right. Now, the reason he put these spring-loaded doors at the end of the alley was not to aggravate the rats, but to be able to control the path they took on the first trial. He could selectively lock some of these doors while leaving other doors unlocked. And that's demonstrated in this example that I have on the screen in front of you now. On the very first trial, what he did was at the critical choice points in the maze, he locked all the doors. These are the doors that I've specified in red here. He locked the doors at the critical choice points where the animal could go wrong to prevent any errors on the first trial. And only the choice points that led to a successful outcome were allowed to be opened. So what would the animal's experience be on the first run through the maze? Well, we started out here and the animal came to this intersection. It could only turn right because the left door was locked. Similarly, when it got to this point, it could only turn left, only turn right, only turn left, only turn left. The animal could not make any errors the first time through the box. So the special conditions in place for the very first trial eliminated the possibility of any errors and allowed only correct turning behaviors while traversing the maze. So what Goodrick believed that this would do is it would establish this, it would essentially take advantage of this response perseveration behavior, whatever that might be in older animals, and give the older animals a leg up on subsequent trials through the maze. He predicted that when you took young animals and older animals and gave them this first trial experience where they could make no errors, and then on subsequent trials unlocked all of the doors, that the older rats would learn faster. They would require fewer trials, fewer runs through the maze to successfully complete the maze without any errors. And indeed, that's what he found in the study. The older rats outperformed the young rats. So that's evidence that the response perseveration of these animals that was built up on the first run carried through to the subsequent learning experience in the, if you will, in the multiple choice maze. When the same experiment is conducted without that special first trial, the young rats always do better than the older rats. However, it's only in this special case that we see this reversal of the age effect. And if we want to take this and maybe speculate a little bit about what it might mean for human behaviors, one of the things I think it means is that I have this note down here in green. One of the common ways that we learn to do new things is using the trial and error technique. And so we try doing it this way, it doesn't work, we try doing it that way, etc., so to speak. This type of response rigidity tendency in older people would suggest that perhaps the trial and error technique is really not the way to go as a strategy when you're working with older learners. And what we'll see at the very end of the presentation module on learning conditioning is I'll say a few words about an alternative approach, and that's a modeling approach, an observational learning approach that seems to be very, very powerful from the perspective of older learners. And I promise to get back to that by the end of this lecture series. So now we ask the question, does response rigidity that we saw in rats characterize behavior in older humans as well? And it's not appropriate to use T-maze to study humans, but there are several other learning and problem-solving domains that have been studied that have yielded support for this response rigidity hypothesis in older humans. And one of the most interesting research areas that has demonstrated this type of response rigidity in older humans, at least I find it interesting, are some studies that have used the water jug problem. And there's quite a influential study that was done by Hegelin using water jug problems that indeed demonstrated quite compelling response rigidity, or if you will, behavioral inertia in older animals compared to their younger counterparts. So before we can go ahead and look at this water jug experiment, let's get a little bit more familiar with the water jug problem in general. And what I'd like to do at this point is I would like to give ourselves a little bit of room to breathe here, a few minutes to breathe, by looking at a very difficult water jug problem that was encountered in a very famous Hollywood film. That is one of the Die Hard films. So let's take a look at how Bruce Willis and his colleague try to solve this important water jug problem while they have the essentially sword of Damocles hanging over their head. And after viewing that problem being solved, we'll review it and then take a look at a study that examined how young and older people approach solving these water jug problems.
Be careful. Don't open it.
What? I gotta open it. And it's gonna be all right.
Shit! I told you not to open it!
I trust you see the message. It has a proximity circuit, so please don't run.
Yeah, I got it. We're not gonna run. How we turn this thing off?
On the fountain there should be 2 jugs. Do you see them? A 5-gallon and a 3-gallon. Fill one of the jugs with exactly 4 gallons of water and place it on the scale, and the timer will stop. You must be precise. 1 ounce or more or less will result in detonation. If you're still alive in 5 minutes, we'll speak.
Wait a sec! I don't get it. You get it?
No.
Get the jugs. Obviously, we can't fill the 3-gallon jug with 4 gallons of water, right?
Obviously.
All right, I know. There we go. We fill the 3-gallon jug exactly to the top, right?
Uh-huh.
Okay, now, we pour that 3 gallons into the 5-gallon jug, giving us exactly 3 gallons in the 5-gallon jug, right?
Right.
Okay.
Then what?
Now, take the 3-gallon jug, fill that a third of the way up.
No, he said be precise.
Shit.
Exactly 4 gallons.
Copping 50 miles is running his ass off, and I'm out here playing kids' games in the park.
Hey! You want to focus on the problem at hand? Oh, shit! We got less than a minute. Throw this thing away.
Look, we can't take it off and it'll detonate. Just wait a second. I got it. Exactly 2 gallons in here, right?
Right.
Leaving exactly 1 gallon of empty space, right?
Yeah.
A full 5 gallons here, right?
Right.
You pour 1 gallon out of 5 gallons into there, we have exactly 4 gallons in there.
Yes.
Pour it in there, come on. Come on. Don't spill it. Good. Exactly 4 gallons.
You did it, McLean.
Put it on the thing, get it down there. Shit.
Okay, so we saw Bruce Willis tackling this water jug problem, and to summarize what he needed to do in the bottom part of the slide here, he was given a 5-gallon jug and a 3-gallon jug and a limitless supply of water and given the task of measuring out exactly 4 gallons. Not approximately 4 gallons, exactly 4 gallons. So how would he go about solving this problem? And what I have here is a set of steps we could go through to solve the problem. And what you should keep in mind is this isn't the only way the problem that could be solved, but this is one way that it could be solved. So see if you can follow along with me as we go through the process. So we start out with 2 empty jugs, and in our very first step, what we do is we fill the 5-gallon jug all the way to the top using our external water source. So now we have 5 gallons in the 5-gallon jug and 0 gallons in the 3-gallon jug. Then we take the 5-gallon jug, which is full, and we pour its contents very carefully into the 3-gallon jug. And after doing that, we're left with a state where the 3-gallon jug is full, and we know we have 2-gallon residual left in the 5-gallon jug. So at that point, what we do is we dump the contents of the 3-gallon jug. And we know that we now have 2 gallons in the 5-gallon jug and 0 in the 3-gallon jug. So now what we do is we carefully pour all the contents of the 3-gallon jug here into the 5-gallon jug into the 3-gallon jug. So now we know we have an empty 5-gallon jug and we have 2 gallons in the 3-gallon jug. How do we know we have 2 gallons in the 3-gallon jug? Because we took the full contents here and transferred them to the 3-gallon jug. So now what we do is we fill up the 5-gallon jug, right? So we know we have 5 gallons here and 2 gallons here. And then in the final stage, we carefully pour some of the water from the 5-gallon jug into this empty space in the 2-gallon jug, which we know must be what? 1 gallon. 3 gallons minus 2 is 1 gallon. And we know now that we're left with a residual of 4 gallons in the 5-gallon jug. And that's the solution to the problem. Unfortunately for us in the film, they skipped all these steps and proceeded just from the second from the last step. My guess is probably the director filmed the whole sequence, but it was probably too long and boring, and so they just cut it all out on the editing floor to make the scene more compelling and dramatic. Okay, so let's take a look at a demonstration of response rigidity in older adults. And there have been many studies that have demonstrated this type of rigidity, or sometimes called cognitive set or cognitive inertia. But among most famous examples are the case of Hagelin's water jug problems. So let's look at a 2-problem sequence that one would typically observe in the groups of water jug problems that young and older problem solvers or learners were presented with. So here we see problem N, and we're immediately following it is problem N+1. So we look at problem N. It's what you're given are 3 water jugs. They're called jugs A, B, and C. And in this case, they contain 21, 127, or 3 quarts. And now you're told you need to measure out exactly 100 quarts. So if you see, this has the same characteristics, this problem, as the Die Hard example, except now instead of just being given 2 jugs, you're given 3 jugs. And the solution to this problem that's derived at by most people is you take B, 127 gallons, you subtract from that A, so you fill B with 127 gallons, you pour that into essentially the 21-gallon jug, and then you proceed to take what's the remaining contents of B and 2 times dump it into the 3-quart jug C. And that leads to a sequence of 127 minus 21 minus 3 minus 3, and that's your solution. You get exactly 100 quarts. Now, the interesting thing is not the solution of that problem per se, or the strategy per se you use, but what happens in the very next problem in the pair. So we take a look now at problem N+1. We see that we're given 3 jugs, A with 23 quarts, B with 49 quarts, and C with 3 quarts. And we're tasked with measuring out exactly 20 quarts. Well, one way we could solve this problem quite easily is to start with A, 23 quarts, and just pour 3 quarts into C. That would give us 20 quarts exactly. That's the most straightforward and easy solution to this problem set. However, very frequently in older adults, when this problem follows the previous problem with the solution B minus A minus 2C, the older problem solvers or learners reapply the same strategy. It's as if they have a certain cognitive set, a certain response rigidity. Gee, they found a solution in the previous problem, they stick with that solution even though it's somewhat inefficient, in this case, very inefficient. It works, but it's certainly not optimal. And when there are many of these types of pairs of problems in the set of water jug problems, what we see over and over again is that the younger subjects rarely have this cognitive set response rigidity problem of over applying a previous strategy, but it's instead quite commonly observed in the older adults. And there are many other types of studies that also show this qualitatively distinctive characteristic of learning in older adults, this, if you will, response rigidity, response perseveration, cognitive set, cognitive inertia, whatever you want to call it.